In section 9.4, we're going to be talking about arithmetic series. So a series, by definition, is an indicated sum of terms in a sequence. So basically, we're taking a sequence and we're adding up all the terms together. That's what a series is. And there are two different types of series: finite series and infinite series. A finite series, clearly pretty much by the name, ends. And if you want to think about it in terms of a TV show or TV series, you could think of a show like Breaking Bad, because that had a super definitive, clear-cut ending. There's not going to be any sequels. It was done after, like season 5, and that was it. Infinite series is something that never ends. It doesn't have a definitive end to it. So you could think of, in the same comparison, like a soap opera like Days of Our Lives. That show has been going on forever with no end in sight. A show like Grey's Anatomy also has pretty much been going on forever with no end in sight. So just kind of comparing the two. The names make it pretty obvious, but that's kind of what they mean there. Finding the sum of an arithmetic series. So the sum, and we denote that as a capital S subscript n, of a finite arithmetic series a1 plus a2 plus a3 plus all the way to my last term an is n over 2 times a1 plus an. And this formula is going to be super important, so definitely make sure you have this written down, highlighted, starred in your notebook. And let's break down what all these terms mean. A1 is your first term, an is your last term, and n is the number of terms in that series. So here, let's find the sum of an arithmetic series. What is the sum of even integers from 2 to 100? Now, this is clearly finite because this is countable. I could count all the even integers from 2 to 100 if I wanted to. And to easily be able to find the sum of this, I'm going to use my formula. My first term I'm using is 2, and I'm going all the way up to 100, so that's my an term. And thinking about my n value, how many even integers are there from 2 to 100? Logically thinking about that, I know that there are 50 even numbers from 2 to 100, so that's what I'm going to plug in here. Now all I have to do is let my calculator do the work. 25 times 102 is 2,550. And this saved us a lot of time because, you could manually just count 2 plus 4 plus 6 plus 8 plus 10 all the way up to 100, but that would take you a lot of time. So formulas like these can be really, really helpful. So let's look at a real-world example to see where this could kind of come into play. In example number 2, a company hypothetically pays a $10,000 bonus to salespeople at the end of their first 50 weeks if they make 10 sales in their first week and then improve their sales numbers by 2 each week thereafter. One salesperson qualifies for the bonus with the minimum possible number of sales. So, judging by that information, we want to figure out how many salesperson did that person make in week 50? And finally, how many sales did they make overall in all 50 weeks combined? So to find the first one, to find out how much they made in week 50, we're going to first need to know our A1 value to be able to create a formula. So our A1 value is 10 because you have to make 10 sales in your first week. And I know that my common difference, or D value, is 2 because I'm adding 2 sales each week. Also, since I'm adding 2 sales each week, I know that this is going to follow an arithmetic sequence. So now, I have my A1 value, I have my common difference. I'm going to be able to make an explicit formula, which is very similar to what we did all the way back in section 2. My explicit formula for an arithmetic sequence is A sub n is my first term plus n minus 1 times d. I want to find the 50th term here for how many sales you made in week 50. Plug in my A1 value and my D value, plug that all into my calculator, and I'll figure out that in week 50, that salesperson made 108 sales. Now, knowing that 50th term is going to be helpful to find out how many sales they made in all 50 weeks combined. Since I want to find the summation of how many sales they made from week 1 to week 50, I'm going to use that new formula that we learned. So my summation is n over 2 times a1 plus an. Again, I'm trying to figure out how many sales we made in week 50, so there's 50 terms here. In the first week, you make 10 sales. In the last week, we had just figured out you make 108 sales. Plugging that all into the calculator, 25 times 118 equals 2,950. So I can conclude that this salesperson over all 50 weeks made a total of 2,950 sales. Another way that we could look at these is something called summation notation. And this can get a little bit confusing, so just make sure that you're taking good notes here. So we use a Greek letter sigma to also indicate a sum. So for example, let's say we have this sequence here. So 3 squared plus 4 squared plus 5 squared, and I'm going all the way up to 108 squared. If I want to represent this in sigma notation, this is how I would go about it. I'm starting with n equals 3, I'm going all the way up to 108, and I have n squared for my formula. So let's break this down. N equals 3 is my lower limit. Now that's not my A1 value. My A1 value here would be 9, but I'm plugging in 3 for my first term. So I would call n equals 3 my lower limit. 108 is my upper limit. Notice that my A sub n value would be 108 squared, but I'm plugging in 108, that's like my nth term there. Finally, my explicit formula here is n squared because it looks like I'm starting with 3, ending with 108, and I'm squaring that number each time as I move up by 1. Finally, something that's going to be important here is to find the number of terms. How you do that is you do your upper limit minus your lower limit plus 1. So for example here, the number of terms in this sequence is 108 minus 3 plus 1, or 106. So let's look at an example here. So here I want to find what is summation notation for the series 7 plus 11 plus 15, and I'm going all the way up to 207. What I'm going to want to figure out first, or what I'm going to be able to do here, is figure out an explicit formula. So first let me just write out for an arithmetic sequence a1 plus n minus 1 times d, and let's just plug in what we know. It looks like I'm adding 4 each time, so that's my common difference. I'm starting with 7, so I'm going to plug that in. And just to kind of clean it up a little bit, I'm going to distribute that 4. My explicit formula is 3 plus 4n. And this is going to be important because I'm going to use that to figure out what like my upper limit is and then finally kind of work backwards in my lower limit. So I see that I have 207, but what did I plug in to get 207? 207 is my last term that I get. So a sub n is 207, and I get that by using the formula 3 plus 4n. So I'm going to work backwards to find n. And that's going to be my number of terms. So I get 204 divided by 4. So 51 equals n. That's the number of terms that's in that series, and that's kind of my upper limit here. Also, when I work backwards, I could figure out that my lower limit is 1, because if I have 7 equals 3 plus 4n, 4 equals 4n, 1 equals n. So that's kind of where that goes. My upper limit we found out was 51. And my explicit formula is 3 plus 4n. So that's my answer. Working the other way, here I'm giving you summation notation, and I want you to find the sum of this series. So it looks like my lower limit's 1, my upper limit's 70, and my explicit formula is 5n plus 3. The key here is finding my a1 and an values. To find a1, I plug in my lower limit to my formula. 5 plus 3 is 8. Same thing to find my an term. I plug in 70 because that looks like my upper limit. 5 times 70 plus 3 is 353. And now I can use my summation formula here. My number of terms is 70, my upper limit minus my lower limit plus 1. So that just ends up being 70. And then I do 8 plus 353. I plug that all in. 35 times 361 gives us 12,635. And I'm done.